Hi, this is Brittany Jackson, and this is my restructured video on rationals under multiplication. So before I get into this, I just really quickly wanted to point out, because I am doing a unit on rational polynomials, I wanted to point out that the word rational, it doesn't just mean that we're dealing with rational numbers, but that we're dealing with ratios. We're dealing with fractions. So let's take a look at an example. So here we have a whole number times a fraction, 6 times 3/4. So we should know that we can rewrite 6 as 6 over 1. We can rewrite any whole number as itself over 1. We also can, we should recognize the pattern that when you multiply fractions, you are just multiplying your numerators and denominators straight across. So in our new numerator, we would have 6 times 3 and 1 times 4. We can also break any of our composite numbers down. Remember, composite is just any number that has factors other than 1 in itself. So I see two composite numbers here. I see 6 and I see a 4 that are composite. So we can break 6 down, and I like to use my prime factor tree. So 6 is 3 times 2, and 4 is equal to 2 times 2, and 3 and 2 are both prime. So instead of 6, we can substitute 3 times 2, and instead of 4, we can substitute 2 times 2. So we would have 3 times 2 times 3 over 1 times 2 times 2. So we don't have to do anything from here. Here we can break this back apart if that helps. You visualize we have 3 over 1 times 2 over 2 times 3 over 2. And our multiplicative inverse tells us that this 2 over 2 just becomes a giant 1. So we don't want to say cancel out, but I will draw a 1 through it to show that it becomes a 1. So now we have 3 over 1 times 1, right? Anything times 1 is just itself, so this adds no value. So that's why we kind of can say cancel out, but instead of canceling out, we'll just say that this creates a 1 pair, and it just doesn't add any value to our problem, times 3 halves. So now that we've created that 1 pair, we can kind of ignore it because, again, it doesn't add any value. We have 3 over 1 times 3 over 2. And again, multiplying our numerators and denominators straight across, we have 9 halves as our final answer in reduced form. And the reason that this is in reduced form is because we did our prime factor tree to find the common prime factors. Let's take a look at this example. Here we have something a little more complicated. We have a fraction times a fraction. So we have 7 over 24 times 30 over 49. So again, we should recognize that pattern that when we're multiplying fractions, that we will just be multiplying our numerators times our denominators. So in our numerator, we'll have 7 times 30, and in our denominator, we'll have 24 times 49. So here is where, again, I like to break this up using my prime factor tree. 30, 24, and 49 are all composite, so I can break those down into our prime factors. So 30, we can rewrite, we know 30 is 15 times 2, 2 is prime, so we circle it. 15 we can break down into 5 times 3, which are both prime. So that means that 30 is equal to 2 times 3 times 5. For 24, if we break that down, 24 is equal to 8 times 3. 3 is prime, so we circle it. 8 is equal to 4 times 2. 2 is prime, so we circle it. And 4 is equal to 2 times 2, so we circle it. So that means that 24 is equal to 2 times 2 times 2 times 3. 48 is composite, so we can break it down. 48 is equal to 7 times 7. 7 is prime, so we circle it. So 49 is equal to 7 times 7. So let's take this information and substitute these factorizations in for our values in our problem because they are equivalent. So in our new numerator, we will have 7 times 2 times 3 times 5. In our new denominator, we will have 24, which we said was 2 times 2 times 2 times 3, and that's times 49, which we said was times 7 times 7. Okay, so here I'm just going to highlight this, right? These are our factors of 30. These were our factors of 24, and these were our factors of 49. So now I can rearrange multiplication, right? Multiplication is commutative. That means that I can, the order doesn't matter, right? 2 times 3 is equal to 3 times 2. They both equal 6. It doesn't matter if the 2 or the 3 comes first. So we can rearrange all of these numbers because multiplication is commutative. So I'm going to rearrange these so that way, if possible, I have the same number over the same number so I can create a one pair and possibly make this problem a little bit simpler. So I'm going to rewrite this problem. So I see I have a 7 in my numerator and I have a 7 in my denominator. So I'll put those over each other. So 7 over 7. So those are done. I have a 2 in my numerator, 2 in my denominator. Okay, I have a 3 in my numerator and a 3 in my denominator, so I'll put those over each other. And I think those are all my pairs. So in my numerator left I have a 5, and in my denominator left I have a 2, and a 7. So now when I break this fraction apart again, I will have a 7 over 7, which creates a one pair, right? So let's just draw a 1 through that. Right, that creates a one pair. 2 over 2, that creates a one pair. 3 over 3, that creates a one pair. So all that's left is a 5 over 2 times 2 times 7. So what we're left with is 5 over 2 times 2 times 7. So 2 times 2 is 4. And 4 times 7 is 7, 12, I'm sorry, 7, 14, 21, 28. 28. So this is our final answer in simplified form. And again, it's in simplified form because we simplified each of our composite numbers using our prime factor trees. And we utilize the multiplicative identity of and creating one pairs to make this problem a lot simpler. The last thing that I want to address is a program that I use in my class called Get More Math. So something that was brought up in a couple of the comments on my video was around the idea of repetition being key, having students continuously practice similar problems. And I find that this program is super helpful. If any of you are teachers and interested in this program, I highly, highly recommend it. The whole point is student retention and repetition through and practice, obviously. So if any of you are interested, I believe the first year for any new teachers is free, and it uses a Common Core curriculum, has integrated math curriculum. I definitely highly recommend giving this a look. And if you have any questions about this program, let me know, but I've been using this in my class for years and I love it.